to the lecture number 6, Computational Methods and MATLAB. Today we shall discuss about special matrices. So if you have already seen that when you write help LMAT, that is elementary matrix operation, that is one of the directory in the structure of MATLAB. Apart from the various functions like zeros, ones, I, replicate, tile array, size of the array, display the matrix, etc. I have promised that I shall discuss about some of the specialized matrices. So this is not a course of numerical linear algebra, but as far as concerned, I shall discuss most of them, and a large part also I leave for the viewers so that they can go back and find out from any book on numerical linear algebra or linear algebra. One of the good books which I suggest is Applied Linear Algebra by Gilbert Strang. While solving linear differential equations, right? So I shall tell you about the linear differential equation. Suppose I have an equation like this: dqx by dtq plus a3 a2 d square x by dt square plus a1 dx by dt plus a0x is equal to b. Suppose this is my equation, linear differential equation. So this equation can be written in the form of a state space. For example, I can take that, I shall take x1 to be equal to d square x by dt square. I can take x2 to be equal to dx by dt and x3 to be x. If I take like this, so this turns out to be a third order differential equation. So I can write this as you can see here, x3 dot is equal to x2 and x2 dot is equal to x1 and x1 dot is equal to, from the equations which you can see here, this is your x1 dot. So what I can do is I can write it, I can take everything to the right hand side. If I take to the right hand side, you can see b minus a2 into d square x by dt square, you have taken x1. So a2 into x1 minus a1 into x2 minus a0 into x3. So you are going to get this. So you can write this to be b minus, you can write b. So consider b to be 0 for the time being. For 0, when you evaluate this particular, when you try to solve the differential equation, you have two functions. One is called complementary function, another is called particular integral. And this complementary function is obtained by equating it to 0, is it not? One of the solutions is obtained by equating the whole thing to 0. So assume b to be 0. So in that case, this turns out to be minus a3 into x1 minus a2 into x1, then minus a1 into x2, then minus a0 into x3, right? So minus a2 into x1, as you can see, is it not? And whole divided by a3, is it not? So you will find this will become minus a2 by a3 into x1 minus a1 by a3 into x2 minus a0 by a3 into x. So if you can see this, so if you write this whole thing into a matrix form, you can see, suppose you assume x3, x2, x1 to be some matrix x, let us say this is reverse order, it could have been. So this will turn out to be x dot is equal to, you can write 0, 1, 0, then 0, 0, 1, then minus A naught by A3 minus A1 by A3, then minus A2 by A3, x3, x1, x2 and x1. So this kind of matrix is known as a companion matrix. So why it is companion matrix and what is the beauty of this matrix? You will find if you take the roots of the eigenvalues of this matrix, this will be equal to the eigenvalues associated with this differential equation. So how do you find out the eigenvalues, compute the eigenvalues of this linear differential equation? So the eigenvalues of this differential equation or the roots of the characteristic equation from this differential equation can be written like this. If you take the Laplace transform, or otherwise you write generally the characteristic equation to be a3 d square dq plus a2 d square plus a1 d plus a naught, is it not, into x is equal to 0. So this if you divide a3 throughout, you can write dq plus a2 by a3 d square plus a1 by a3 d plus a naught by a3 into x is equal to 0, where d is the separator, d by dt. So you can say d square is equal to d square by dt square and dq is equal to dq by dt cube. And this whole polynomial is known as the characteristic polynomial of the differential equation. And as you know, from the roots of this characteristic polynomial, you can find out the solution, one of the solutions of the, that is complementary function, is it not? So you can find out the complementary function using the roots of this particular polynomial, and the roots of this polynomial is equal to the eigenvalues of the companion matrix. So there is a very strong correspondence between the companion matrix and this. So finally the companion matrix I will define like this. So a companion matrix you can say can be obtained by a vector u. Suppose you write a vector u which is representing the roots, sorry, the coefficients of a polynomial. Suppose I write the vector u to be like this. That means this represents a polynomial px which is equal to, you can write, this is a, these are 4 coefficients, so it is a third order polynomial. Third order means I can write xq into multiplied by 1 plus 0 multiplied by x square, is it not, minus 7 multiplied by x plus 6. So this is the polynomial, or in other words xq and this term is absent, 7x plus c. So this is the coefficient of this polynomial, and if you say the companion of u, the MATLAB command is companion of u, this will generate a matrix which will be equivalent to that, whose first row, suppose this is u, so whose first row will be u 2 colon n slash u1. There it was the last row, here it was the last row, it can be easily written in this form, this can be easily written, this last row, this you can just reverse, you can reverse if you write x1 dot, x2 dot and x3 dot, if you write like this, this will be, if you put x1, x2, x3, so this whole row will be interchanged, so this will be minus a0 by or a2 by a3, right, then minus a1 by a3, then minus a naught, just I will write once again. So you can see this particular slide, that is from this differential equation, if you write, this is the differential equation, that is a3 dqx by dtq, once again I am writing, plus a2 d square x by dt square plus a1 dx by dt plus a naught into x is equal to 0. So you are writing like this, you are writing the first row to be, so you are writing in this form, you are writing that x1 x is equal to x1, then you are writing dx by dt to be equal to x2 and d square x by dt square is equal to x3. Slightly changed. I have slightly changed. So in this way you will get x1 dot to be equal to x2, x2 dot will be equal to x3 and x3 dot will be equal to, just put it here, you will get minus a2 by minus a0 by a3 into x1, then minus a1 by a3 into x2, then minus a2 by a3 into x3. This is the one you are trying to get, is it not? So if you write in the matrix form, so you get actually x1 dot, x2 dot and x3 dot. You can write x1, x2 and x3 here. So here you write 0, 1, 0, then you write 0, 0, 1, then you write minus a0 by a3, then minus a1 by a3, then minus a2 by a3. So this matrix is the companion matrix. You can interchange the rows and columns. So here again I will cast the definition. So the first row, actually we will change the last row into the first row. So the first row of the companion matrix, if you write u as the coefficients of polynomial which I have taken as example 1, 0, minus 7, 6, then the first row will be minus u 2 colon n divided by u1. As you can see here, this could be also last row or first row, doesn't matter, it will not change anything. So you can see this is u2 to n, that means it will take from here to here, then it will divide it by the first, that is 1. So that means it will be a 3 by 3 it will be it will having 3 elements, because n is equal to 4 here, is it not? So it will have 3 elements, the first row. So you can write the first row of that matrix A, let us say, to be 0 divided by 1, minus 7 divided by 1, then 6 divided by 1, and the next rows will be like this, like 1, 0, 0, 0, 1, 0. It is like reversing this. If you take, that means if you interchange this whole thing, that means if you make x3 dot, x2 dot and x1 dot, the way you will write here will be interchange, because this whole thing will, this whole row will come up and there will be interchange, is it not? So that is the companion matrix. So that is what happened here, right? So now the point is, what is the characteristic equation of this? That means if you find out the eigenvalues of this matrix, that will be lambda I minus a, then determinant of this has to be equal to 0, then find lambdas for which it is satisfying, is it not? So let us see in MATLAB how, whether it is working or not. Let us find out a polynomial whose roots are this, then find out the corresponding companion matrix and see the roots of that companion matrix, that's the eigenvalues of the companion matrix. Let's see that. So look at the screen. So let us take a polynomial. Just now we have taken u, let us say u is equal to, you said that it will be 1, 0, minus 7 and 6. Okay, then you know the roots of the polynomial having, this is the roots of the polynomial having coefficients u. So minus through to 1. So let me construct the companion matrix. Companion matrix of the polynomial. This is the companion matrix. So find out the eigenvalues of this matrix. See, right? So you can see the eigenvalues of the matrix and the roots of the polynomial, they are same. So companion matrix is very closely related to the polynomial, right? So then the next matrix we will discuss is called Hadamard matrix. It is called the Hadamard matrix. So this is a matrix which is used very much in signal and image processing. The rows and columns of this matrix are having two values, either 1 or minus 1. If you remember Fourier transform, what is Fourier transform of a signal or a function? If there is a function f t, you can decompose the function into a series of sines and cosines. If it is a periodic function, then you call it Fourier series. If it is not a periodic function, then you call it a Fourier integral. So if ft is a periodic function, you can write, for example, suppose I have a function like this. Let's say, let's go to the, suppose I have a function like this. This is a function which is a periodic function, which is goes on. This is function t and this is function of t. So this function is not continuous. This is a continuous function but not differentiable. It is a triangular wave, is it not? So this function can be approximated in a Fourier series by a sinusoidal, is it not? Then you can also, this is the first fundamental, then you can take, so lot of other terms of higher harmonics, is it not? This, if you remember Fourier series. So this is approximating a function by a series of sines. So if it is so, you can also approximate the same function by a series of functions which looks like this. One function like this, that means then another function just double of this, another function maybe half of this, something like this. That means you can represent this whole thing like a staircase. And this staircase representation is possible only when you have functions which looks something like this, or slightly expanded form, double the period or half of the period. So these functions are known as Walsh functions. And this Hadamard matrix has a very close association with Walsh functions. So you can construct, so you don't have to worry about this. So you have to go in detail about Walsh functions. So that means just as in Fourier series you can approximate any waveform by a series of sines and cosines. Similarly, in Walsh transform you can approximate any function by a series of, you can say, square waves, rectangular waves having different periods or integral periods. Suppose you have a function like this. You have a function something like a sine wave. Let us say this is a sine wave. Suppose I want to approximate it by series of infinite series of rectangular waves. I can do so. What I'll do is I will take one wave like this, then another wave I can take like this, so that I can approximate, then another wave like that, so that I can approximate like this. That means as a sinusoid can be used to approximate discontinuous functions, similarly a discontinuous function like this Walsh function can be used to approximate any of these functions. So what is the advantage of this function? This function has a lot of advantage when you talk about compression, signal compression, image compression, when you talk about sampling, quantization. So this function has a lot of use. So from this function, what is done is you have a matrix, and that matrix is Hadamard matrix. So if you construct an Hadamard matrix H, the MATLAB function command is Hadamard n is the dimension of the matrix. You will have a matrix H whose rows and columns will be orthogonal to each other. That means if you take this as to be H matrix having rows and columns, if you take H transpose H, it will become an identity matrix, right? So this is very much used in combinatorics, signal processing and image processing, especially closely associated with Walsh transform. You can see here, suppose you look at the screen. So I'll write H Hadamard for, you can see this is a symmetric matrix and H transpose H is equal to identity matrix. But of course, you have to divide it by the order of the matrix, that is 4. So that means H transpose H by 4 will give you the identity matrix. So this is called Hadamard matrix. So then the next matrix which we are going to discuss is called Hankel matrix. Next function which we will discuss is the Hankel matrix. So, what is an Hankel matrix? Generally, Hankel matrix is defined by two vectors, vector C and R. So, if you write in MATLAB Hankel C and R, it will return you a symmetric matrix. It will return you a matrix, actually not symmetric matrix, it will return a matrix whose first column will be C and first row will be R, right. So, whose first column will be C and last row will be R. The last row, this first column will be C, this is the first column, and last row will be R. Then you must be thinking that the last values of C and the first values of R should match. If they don't match, then the last element of C will prevail. For example, suppose I have a vector like this. Let us say C is equal to 1, 2, 3, and R is equal to say row vector 7, 8, 9, 10. Let us say, right. So, if you write Hankel CR, what will happen? The first column is 1, 2, 3, but last row will be the R. This is the last row, but because this 7 is different from 3, therefore 3 will be preserved. Then rest of them will be 8, 9, 10. Then this will become symmetric. So, therefore 1, 2, 3. So, 2, 3 will come here, then comes 8 here, then 3, 8 will come here, then comes 9, so on and so forth. So, Hankel matrix, once again, because to construct an Hankel matrix, Hij, you can say, that is the ijth element of the Hankel matrix will be equal to P I plus j minus 1, where P is a vector, which is given by C, then R 2 to end. So, first you construct this vector, row vector, you can say C R 2 to end, then calculate Hij. Suppose this is H or H, you can say. So, the Hij, that is ijth element, will be this. So, Hankel matrix appears in many signal processing applications and approximation cases, where you will find you generate an Hankel matrix. And if you write Hankel CC, so this matrix will be there. If you write Hankel C or Hankel CC, just Hankel C, it will give you a symmetric matrix. So, you have to first construct the P, which is C, then C2 to end, then this is H, let us say, then the ijth entry of that particular H matrix will be P I plus j minus 1. So, this is the way you construct the Hankel matrix. Let us consider here, let us look at the screen. So, if you look at the screen, take some C, let us say, take C, let us say C, you take 1, 2, 3, 4, okay. So, write Hankel C. So, you can see this is the Hankel matrix, and one more thing is all the elements will be 0 below the in case of, if you give Hankel just C, you will find all the elements below the anti-diagonal will be 0. Okay. If you write Hankel CC, then it will give you a symmetric matrix. That means it will give you a matrix whose Hankel CC dash, because one is a row matrix, one is a column matrix, Hankel CC dash. So, what you get is you will get a symmetric matrix. So, you can see 1, 2, 3, 4, 2, 3, 4, 2, it is just rotated, then 3, 4, 2, 3, 4, 2, 3, 4. So, this is the principle of Hankel matrix. For more information, please refer to any numerical linear algebra book, right. So, then the next matrix in our row is Hilbert matrix. So, you can see Hilbert matrix. So, this is a typical matrix. Suppose you write H is equal to Hilbert n. So, n is the number of, is the dimension, you can say, or order, you can say order. So, it will generate an n cross n matrix whose elements ijth entry of the element will be given by this formula. So this is the ijth element. So this will be a symmetric matrix because this will be equal to h j I, is it not? So this is a symmetric matrix, and this is a matrix. Is this what is the characteristic of this matrix? The characteristic is it is a very yield conditioned matrix. What is yield condition? That means the largest eigenvalue of this matrix and the smallest eigenvalue of the matrix, they differ by a very large factor. So that makes the matrix yield condition. As you know, the rank of a matrix is given by the determinant, and the determinant is equal to the product of eigenvalues. Remember, the determinant of a matrix, square matrix, is the product of the eigenvalues. So if this is the product of eigenvalues, suppose this is a square matrix. So what will happen is, if one of the eigenvalues is very small, that means the determinant is very close to 0. That means the matrix is having rank deficiency. If this is the case, then matrix can be yield conditioned, is it not? If the eigenvalue is too small, that means the matrix is supposed to be yield conditioned. So these Hilbert matrices are symmetric matrices, but they are yield conditioned matrices. So why do we need such a matrix? This matrix is required to test some of the very robust eigenvalue analysis algorithms or eigenvalue computation algorithms. People every day eigenvalues, and you have got a new eigenvalue computation algorithm, and these eigenvalue computation algorithms are very important because eigenvalues are important. Why the eigenvalues are important? Because eigenvalues represent the characteristic of the matrix, and the matrix may represent a system, then it represents the characteristic of the system. If the matrix is representing a signal, then that eigenvalue is the characteristic of the signal. So what could be the characteristics of a signal? Could be a frequency, information about the frequency component, frequency distribution, power spectral density, so on and so forth. So if you see the Hilbert matrix, let us see the eigenvalues, how it look like on condition number. So if you write H is equal to, let us say I am generating a 4 by 4 Hilbert matrix. This is the Hilbert matrix, as you can see. This is a symmetric matrix. You see the eigenvalue of this matrix. One eigenvalue is 0.001 and the largest one is 1.5002. So if you see the condition number 1.551400. But so if your condition number is poor, if you generate another matrix, let us say write H is equal to Hilbert 5. Okay. So if the condition number of this matrix will be poor, as you see, very high. So if I write IH, that is inverse of the Hilbert, this will give you. So inverse of Hilbert is HI, HI into H is identity. That is fine. But if you generate a large matrix, let us say H Hilbert, use 20, and if I write H, so then do, so you write HI into H minus I of 20, norm of this. So what I did is, you look at me. First I took an H, that is Hilbert 20 by 20 matrix. Then I found out the condition number of H. You can see it is very bad condition matrix. You can see 18. That means the largest eigenvalue to the smallest eigenvalue is 10 to the power 18. So if I calculate the inverse by conventional MATLAB subroutines like this is my inverse. It is showing the condition number is poor. Therefore, such matrices cannot be normal inversion routines will not work for the such matrices. So you have to go for like inverse Hilbert. So you can write HI is equal to in Hilbert H. So this is a special algorithm which will find out inverse Hilbert. 1 minute. All, so H is equal to, so this is Hilbert. So HI I can write in Hilb H in will be h, that means in will you have to just specify the number because it will automatically take. So you can see hi into h will give you condition number, that is hi into h. So you can see the norm of hi into h should be identity. So if you subtract the identity matrix, the norm turns out to be very high, right? So therefore this is not working, right? So in the therefore we have to use special subroutines for finding out the inverse Hilbert transform. Just see the help of inverse Hilbert transform. So inverse Hilbert matrix gives you, so whose elements are I plus 1 by upon I plus j minus 1, then Hilbert will give you so another matrix whose rows are 1 plus j minus 1. So the result will be good for n less than 15, but we have taken n is equal to 20, so that's why it did not work. Anyway, so you are now sure that why you need Hilbert matrices. That means I can write, let us say A is equal to Hilbert 5 and B is equal to inverse Hilbert 5. So if you multiply A into B, you will get identity matrix. So that means Hilbert matrix cannot be, you cannot use normal inversion routines for Hilbert matrix. You have to use special algorithms. So inverse Hilbert is one of the algorithms, and the results are accurate only when the dimension is less than 15. So I made a mistake by putting 20. So now the next matrix is magic. So magic matrix is very easy. So magic, it is the magic square matrix which generates magic square. What is a magic square? Magic square is a square matrix. So this is M, suppose you write magic n, so it will give you an n cross n matrix whose elements are constructed from the integers varying from 1 to n to the power 2 with equal row and column sums, right? So n must be greater than 3. The condition is n must be greater than 3, right? So you can see, suppose you write some A is equal to magic, let us say 5. This is this. So if you write sum A in first dimension, you will get a vector all 65. Sum A in the second dimension, you will get 65, right? So therefore the, if you add the row wise and column wise, they will be all equal. So this is the matrix, magic matrix. That's okay. So then the next matrix which we will discuss is Pascal matrix. Okay, let me discuss some other matrix. Pascal matrix I will take up later on. Let me discuss a matrix which is known as Rosser matrix. This is called Rosser matrix. So what is this Rosser matrix? So this matrix is a challenge. Okay. If you see the Rosser matrix, this matrix is a challenge, and this matrix is a challenge for whom? This is for challenge for eigenvalue computation algorithms, symmetric eigenvalue computation algorithms. So if you are going to invent, as you know, eigenvalues are determined by something, some kind of QR factorization or modifications of it. But the symmetricity of a matrix can reduce the complexity of this algorithm manifold. That means the complexity can be really reduced to a great extent. So when the matrix is symmetric, you would like to invent a new algorithm. So you have to test that algorithm, whether that algorithm is robust for numerical instability. So for example, the Rosser's matrix has some peculiar eigenvalues. You can see this. So you write Rosser. This is the matrix, Rosser matrix, you can say. If you see the eigenvalues of this matrix, these matrices, these eigenvalues are very closely spaced. You find there is a double eigenvalue. If you see, if I write V is equal to eigenvalues of this matrix A, and if you see, if you just bar plot this V, that is you are looking at the bar chart of V, what you can see here is there is a small non-zero eigenvalue here. As you can see here. So this is a so you can see this is your V. So 3 plus 3 plus 2. So there are the number of eigenvalues are 8, is it not? So it's an 8 by 8 matrix. So there will be exactly 8 eigenvalues. Out of 18 eigenvalues, there will be a double eigenvalues. As you can see, there will be a double eigenvalues here. This is a double eigenvalue. There is a small non-zero eigenvalue, that is V2. You can see V2. This is small non-zero, but small eigenvalue, but non-zero. Then you can see V4 and V5, they are same, that is 1000 and 1000. Then there is a dominant eigenvalue of opposite sign, as you can see here, that is minus 1.02. This is a dominant eigenvalue, that is V1. Okay, there is a dominant eigenvalues opposite sign, and there is a small non-zero eigenvalue. There is a small non-zero eigenvalue. This is the small non-zero eigenvalue, and an eigenvalue which is very small, almost zero. This is a zero eigenvalue. There is a small. So what happens? The condition number of this matrix, as you can see, condition number of A is very poor. At the same time, 10 to the power 15, the eigenvalues, two eigenvalues are same. One eigenvalue is negative, one is zero. So what does it imply? In control systems, if you have a system having such eigenvalues, the system becomes unstable. And if you are designing an eigenvalue computation algorithm, you have to test on these matrices like Rosser matrix to whether it is able to get the accurate eigenvalues or not. So this is the reason why Rosser matrix is so important. So the next matrix which you will consider, the next type of matrix is T-Please matrix. T-Please matrices. What is a T-Please matrix? Let me give you the definition first, then I will get into the details. Similar to Hankel matrix, it has got very close association with Hankel matrix. It is similar. You can see here, if I write T, the MATLAB command T is equal to T-Please C and R. Again, C is a column vector and R is a row vector, or just you can say C is one vector and R is one vector. So it will give you a non-symmetric T-Please matrix. Generally, T-Please matrix is symmetrical, but if you write like this C and R, it will give you a non-symmetric T-Please matrix. So C will be the where the C vector, the whole vector will be the column vector. Even if it is row or column, this will become the first column, and R will be the first row. R will be the first row, and if first element of R and first element of C are not matching, then C will be used. The first element of C will be used. But if you write T-Please only R, then what will happen? It will give you a symmetric matrix. Okay, it will give you a symmetric matrix with R as the column and R as the row. Then the subsequent rows and columns will be given by rotating that R. You can see, you can see here. Suppose I have a vector, let us say R, which is equal to 1, 2, 3, 4, right? So if you write please R, sorry, mistake. So what is happening, you can see. So the first row turns out to be 1, 2, 3, 4, right? And first column is 1, 2, 3, 4. The second, if you come to this block, it will take this 1, 2, 3, then this is 1, 2, 3. Then if you come to this block, so in the first block this becomes 1, 2, 3, 4, this becomes 1, 2, 3, 4. In the next block, you will just take, it will eliminate this 4, then it will take 1, 2, 3, so 1, 2, 3, 1, 2, 3. In the next it will eliminate 3, so 1, 2, 1, 2, then in the next it will be eliminating this. So you will be constructing like, you will go like this, you will go like this, then like this, then like this, then like this, then like this, like this, like this. So this is the T-please matrix. This is a symmetric matrix, and you will see that this will be a positive definite matrix in most of the cases, right? So if you see the eigenvalues of this T-please, okay, this is a symmetric matrix, not necessarily positive definite. So his eigenvalues are all real, because symmetric matrices will have real eigenvalues, right? So what is the significance of this T-please matrix? Let me discuss about with respect to the autocorrelation sequences of a signal. So now I am going to discuss the significance of the T-please matrix. So if you have a signal which has been sampled by some AD converter and it is available inside your computer, let us write that signal in the form of a vector. That is x0, x1, x2, x3, so on and so forth, xn. So prior to that also you will have x minus 1. So that means the signal is available, the samples of signal are available, xk, where k is varying from, let us say, minus infinity to plus infinity. So all these samples are available in the computer. Let us say your computer will have infinite memory. So if the signal is available with you, then you can define something called an autocorrelation sequence. So if there is a signal called xk, the autocorrelation sequence Rm, you can write to be expected value of xk into xk minus m. That means multiply the present value of the signal with a delayed, either delayed towards the left or right, delayed values of the signal, find out the expected value. That means you are trying to find out the correlation of the kth sample with the last mth sample. That means delayed by m. So that, for example, R naught is equal to expected value of xk into xk, that is expected value of xk square. So this turns out to be, if you take expected value of x square, that means mean of the square of all the samples. So that is equivalent to your power, you can say. Similarly, R1 will give you xk into xk minus 1 expected value, is it not? Similarly, R2 will give you expected value of xk into xk minus 2. So R1 gives you the correlation of the present sample with immediate past, or the present sample with an immediate future. Same thing, because it could be xk into xk minus 1, or it could be xk plus 1 into xk, doesn't matter for all k. Similarly, R2 is the correlation between the present sample and a sample which is past to past sample. So it is actually to find out the expected value, you need infinite number of signal samples, is it not? There is a difference between mean and expected. Expected means it covers everything. So generally people find Rm is equal to limit n tends to infinity 1 by twice n plus 1, this is the mean, sigma k varying from minus n to plus n, right, x of k into x of k minus n. Is that clear? X of k into x of k minus n. So that means n tends to infinity means it is covering whole thing, is it not? It is covering whole thing, but generally you will not find, you cannot find this infinite number of samples are not simply present, not feasible. So you will have some finite number of samples. If there are finite number of samples, suppose n is equal to only 64, 64 samples are available. If 64 samples are available, you can calculate R0, you can calculate R1, you can go up to how much? R63, is it not? Because R0 will give you how much, how to calculate R0? You will calculate by calculating x1 into x0 plus x2 into x1 up to x64 into x63. Fine. 1 by the calculated number of turns, 1, 2, 3, 4, whatever is the number of turns, m or whatever. Is it not? Because it is the expected value of xk into xk minus 1, is it not? So expected value of xk into xk minus 1 is x1 into x0, then x2 into x1, then x3 into x2, like that. This is R1, is it not? Then R0 is expected value of, similarly, xk square, that is x0 square plus x1 square up to x64 square, is it not? By 64, is it not? So that is expected value. Similarly, what will be R2? R2 will be expected value of xk into xk minus 2, is it not? So this will be equal to x2 x0 plus x3 x1, you will go up to x64 into x62, is it not? So on and so forth. So you will find R63 will be how much? R63 will be, so divided by 1, the number of turns here, calculate the number of turns. So number of turns is n, let us say. So this is the number of turns nt. So this is how many? How many? You just calculate x2, x0, x3, 2 to 64. So 2 to 64 is 62, 63 samples. So this will be 63, you can say. Okay. Similarly, 2 to 64, so that is 62 samples should be there. 62 samples plus, oh, x1. So you start x1. So there will be 2, 3 up to 1 to 62. So 62 samples will be there. Similarly, for R3 there will be, so this n will be 62. Then for similarly for R3 it will be expected value of xk into xk minus 3. So therefore you will start with, because only 64 samples are available, so you will start with x3 into x1, actually x4 into x1, because it is delayed by, so here is x3 into x1. So x3 into x1, this will become x61. So there will be 61 samples. In this case, it will be x4 into x1, then x5 into x2 up to x64, x64 minus 3, that is x4 minus 3 is 61. So there will be 61 samples. So like that, if you calculate R, let us say 63, R63 will be one term will be there, expected value of xk into xk minus 63. So that will be only one term. So that is x64 into x1. That's all. So you have only x1 to x64. Therefore, you can have autocorrelation sequence which will be having R0 up to R63. So this autocorrelation sequence will be R0 to R63. So using this autocorrelation vector, using this vector, if you calculate one autocorrelation matrix using this type list, if this vector is, let us say, R, you can say, or this is the vector, you can say triple is R, it will give you, or you can write R like this, small r, because we are representing small r as the vectors, capital R are the matrices. So this will be called autocorrelation matrix. Autocorrelation matrix of the signal. So this has got far-reaching results, because the nature of the autocorrelation matrix, is like this. So nature is first of all, this autocorrelation matrix R is positive definite. That means all the eigenvalues of R are greater than 0. Of course, it is symmetric, otherwise it cannot be positive definite. So this is symmetric. Then the eigenvalues of R gives the spectral information regarding the signal. Right? Let us, if I take one signal like sine, let us say I will take one signal S is equal to simple sine 1 to, I can write linspace, just I am writing here inside bracket, I shall start with 0, let me write up to 5 pi. So I will take only 100 points, let us say. So you can say plot S. So it is a sinusoidal thing, is it not? So how many samples are there in this axis? 100 samples will be there, is it not? So there will be 100 samples. So you can find out the autocorrelation sequence of S. So to find out autocorrelation, see, help, write X4. This is called cross correlation. Okay, you can write X core with itself. So that means if you write C is the cross correlation, C is equal to X core S with itself. So if you this is the autocorrelation function, as you can see. So this autocorrelation sequence, as you can see, is giving maximum here. So the number of samples in, so if you see the length of the signal is 100, therefore length of the autocorrelation sequence is 199, that is 200. Why it is 200? I shall, the reason is generally the autocorrelation sequence is represented like this. Here you have seen that it was R0 up to R63. Generally what you do is you make a mirror image, so you represent like this. Then go to R63. So that means, so this R1 and R minus 1 will be same, because delay by 1 or minus 1, they will be same. Is it not? It is like xk into xk minus 1 is same as xk plus 1 and xk. So therefore you can say this is expected value, this is also expected value. 1 is actually xk into 1 is delayed by 1, 1 is delayed by minus 1, you can say. So therefore autocorrelation sequence is like this. So if the length of the signal is n, then the total sequence will be 2 into n plus 1. So in this case it was 64, so it will be 2 into 64 plus 1, that is 129. In this case the signal is 100, therefore there will be, the length will be 199, and it will be symmetric, as you can see from the bar chart. You can see here. So this one represents the R0, this represents the R0, the first one, and slowly you can see, as you can see, it is varying, damping and going away, is it not? So today we will finish here. So we have seen some of the specialized matrices. I am not going to discuss like van der Waals matrices, Pascal matrices, and some of the special matrices which you will get from gallery. You can see use gallery help. You can see number of matrices here. You can see the matrices all written here: Cauchy, Chebyshev, Chow, circulant, element, Clement, comparison. So these matrices are very specialized for special applications. You can get it from any linear algebra book, or you can even try the internet. So I will stop here. So next class we will go to some of the new functions You can see help MATLAB, you go to the basics, just write help, so you can find the basics. Forget about the toolboxes for the time being. If you go to the basics, so you have just finished elementary matrices and matrix manipulation. So we'll go to elementary functions, then we'll go to specialized functions, mat functions, and go so on and so forth. So thank you very much.